So I think this is working. We're going to find out. Then dramatic pause. Yeah, I think this might actually be working. So, hello, this is Kenneth. We're trying a new setup today. So we have a webcam with a microphone on it. We're going to see how that goes. And we've got a schematic here for your pleasure. We're on my actual standard main desktop right now. And we're going to see if I can try and do some board layout tonight, which I've been meaning to do now for like 3 or 4 months. We're going to see if I can crank this out, and then I figured I may as well turn on the stream while I was at it. Which in this case is a little bit silly because it's like randomly a Monday night. So I don't actually expect much of a turnout tonight, but we're going to see how this goes. So we're going to first see if I can maybe get this even on Twitter. That might be something novel. So we're going to spool up here for a second. So don't be too concerned if this isn't exciting yet. We're still working on it. If my internet will cooperate, which it currently is not. Come on. Man. See, what I'm trying to do right now is I'm trying to load up my YouTube Creator Studio, but YouTube's just having a really bad time right now. My channel. No. Creator Studio. Creator Studio. Ready, set, go. Oh yes, thank you. Thank you for that tab crashing. Come on. Video manager. Really? Video doesn't even show up. I'm looking in the wrong place. Is there a link here? Come on. There we go. Okay, we're going to see how that goes. Worst case, nothing. So anyways, hello. Good evening, folks. So like I said, oh, and that's gone. Man, we're trying to get this all set up as everyone gets bored and leaves. Okay, cool. So like I said, the objective tonight is to take this Raspberry Pi sensor hat board that I did the schematic capture on this months ago, and we're going to see if I can get this laid out tonight. I'm not optimistic, mainly because I haven't driven KiCad now in also several months, and so the fact that I'm going to have to still make a package for one of these parts is bad, but so I'm going to kind of fumble my way through this. You guys are going to sit there and judge me at best. Probably just stop watching, and by all means that's fine, because today we're just screwing around on YouTube and or KiCad. But so what we've got here is we've got the Raspberry Pi 40-pin header. We've got 2 LEDs because hey, LEDs are great, and then it's essentially, this is more than anything else a breakout board for a whole bunch of cheap eBay modules. So we've got a BME 280 sensor right here, which is for temperature, humidity, and pressure. We've got a TGS 2600, which is air contaminant, so carbon monoxide, hydrogen, methane, etc. So probably more than anything else, kind of just organics. So that needs both a heater, 5 volts, and then a 3.3 volts that goes through this pretty much like a series pass sense. We've got a GPS receiver, so this is some random cheap GPS value. Yeah, I don't have bit light on the documentation here. This is one of those eBay random cheap GPS breakouts, which I hopefully have documented somewhere. We've got the standard venerable DS3231 real-time clock hats, which I think it's relatively safe to assume is not actually a DS3231, or if it is, there's something wrong with it, because these hats that you can get on eBay and Amazon are cheaper by a significant margin than the actual chip itself. We've got a Mix 4514 NOx and CO sensor on here. So we've got I think red is the output for the CO, and then NOx is for various nitrogen-based oxides. And this chip has this NOx pre-pin. Best I can tell, it's not strictly necessary, but I'm not sure, and so we're going to break it out here as a spare pin, as kind of a get-out-of-jail-free card. So we've got that going for us. Then, since the TGS, which is what? Yeah, so the air contaminants sensor and then the NOx and carbon monoxide sensors, those are analog outputs, as I would assume is the, yeah, so the air contaminants, NOx and CO are analog outputs, and so we have those fed into an MCP 3008 analog digital converter. And so we've got TGS out, red, NOx, and then since we've got an 8-channel ADC on here, we're also hooking up 3 of them, probably maybe more, down to this header down here, where we have a standard 100 thou header that you could interconnect other stuff onto this board, and then optionally voltage dividers, which I figured out these values of 10K and 1.96K as standard resistor 1% series values that give you what, a 0 to 20 volt scale across the 0 to 3.3 volt scale of the VREF on this ADC. Right, and that's actually kind of a relatively challenging thing to do. All right, because you need to use the voltage divider formula, plus you need to be using the resistor series, which is like the preferred values. Let's see. So looking at these values here, so this is the Wikipedia E-series of preferred numbers. These are great because essentially what it is it's a logarithmic geometric series, which is what they use for resistors. And so, for example, when you're dealing with like 5% resistors, they're almost always in this E24 series, which means that every single one of their values is prefixed by one of these values in green, right? And so you'll, like, on a 5% resistor, you'll often see 10 ohms, 100 ohms, 1,000 ohms, 110 ohms. And that's because it's 10% more than the last one. And so 110 and 100, by a 5% tolerance on each, they meet at 105, right? But 5% up from 110 is 115 point, what, 115 point something? 116 almost, maybe? And so, which this doesn't really demonstrate the point well. So 1, 1.1, 1.2, 1.3, and then it's 1.5 because 1.3 and 1.5 are 10% apart. 1.8, 2, right? And so that you'll often see 200 ohms or 2,000 ohms or 200,000 ohms. You'll see 180 ohms, but you won't see 170 ohms because if you want 170 ohms with 5%, you can pick 1.6 or 1.8 and it will statistically be, you know, you'll get 170 sometimes. Sorry. So anyways, so it's looking at the E series for 1%, which 1% is probably, yeah, E96. So in the E96 series, I had to figure out two resistors that on a voltage divider gave me 0 to 20 as 0 to 3.3, which in this case I settled on 10K by just picking that, and then 1.96. And so if we look on here on the E96, correct? Yes. 1.96 right here, that's a valid E96 1% resistor. So it exists, so you can buy it, which is fantastic. That being said, a somewhat annoying feature is that some of the higher, like, you know, if you're real used to using like E24 series resistors on your 5% and you switch to 1% and you want to pick out the same values, they won't always necessarily be there. For example, 1.2 does not exist in the E96 series. You have 1.21, which is not 1.2. Pragmatically, though, many vendors will sell you tighter tolerances, resistors with tighter tolerances in looser series. So you'll realistically be able to buy E24 series passives with 1% tolerances, which would really dictate that it should be a tighter one. Theoretically, it's supposed to be more expensive because you'll see more volume. They sell more volume in the E96 series 1% than E24 series 1%. For the volumes that hobbyists are buying, I don't think it's ever really proven out to be an issue, so I wouldn't be too concerned. So that's the rationale behind the voltage divider. Why am I doing a voltage divider? Oh, sorry about that. Why am I doing a voltage divider? Because we had some spare inputs left over on this ADC. The first input to this ADC was like a... So what this is all based off of... Let me see if I can find it. This is based off of... some random project that my buddy found. Is it AirPi? Yeah. Sensor hat. AirPi sensor hat. Yeah, here we go. So this is what we started with. So the AirPi was this project where they have this board with a whole bunch of various sensors on there. They released it. It was a Eagle file that you could find somewhere. And so my buddy asked me to fix a few things because I think they got the pin out on one of these sensors wrong. And so I tried to do that for him. And it turned out that kind of the whole board was a bit of a hot mess. Just because, just like me, obviously these guys were hobbyists. And it was, they didn't, it was, I mean, it was, laying out PCBs is kind of an art form, and you'll almost never agree aesthetically with how other people lay out their boards. And we didn't really agree aesthetically with how this board was laid out. So this is me kind of starting over from scratch on a new board design. So that's what's going on. That being said, having the schematic captured, there is the problem that this TGS 2600 passive or sensor comes in a, if I recall correctly, a rather squirrely package, TGS 2600. Survey says TO5. Really? Am I not thinking of the right one? Okay, well, let's assume that that's correct. So then I should be able to check to see if we have a TO5 footprint, which we may not, which may be the issue at hand. And yes, it hanging like that is perfectly normal because that's how KiCad works. So I want, yeah, see, that kind of bodes poorly that that's the only one that I haven't managed to associate yet. So if I were to footprint editor, ooh, come on. TO package through hole. I'm interested in seeing if you have a TO5. Because if we have one, so why in the world did I think, oh, unless, you know, I haven't opened KiCad in a few months, so it's conceivable that KiCad's actually improved their library. Because I know that several of the issues I opened on the KiCad library, on several of the issue tickets I've opened on GitHub, were closed. So maybe this whole evening of me making a new package is actually getting resolved due to the fact that they have actually got the correct package for me. I recall it being a TO25. And so the fact that it says TO5 there makes me feel a little silly. Anyways, I haven't ever actually played with one of these TGS 2600s. It was recommended to me and requested by my buddy that I'm laying this out for. I think the operation of it is conceptually relatively simple. So you've got this, I mean, first of all, you've got a heater, so you need to feed power into it, which just heats up and precharges whatever the sensitive membrane is, and then you bias this sensor, and depending on exposure to gases, the resistance of the sensor changes. And so by setting up as a voltage divider with this other resistor down here, RL, the voltage out will change, and when gases that it's sensitive to are present, the voltage changes. Right. This is a pretty standard way to set up sensors. Anything from, in this case, a gas contaminant sensor to strain gauges, RTDs, resistive thermal devices, thermistors, light sensors, all those sorts of things. But yeah, this really seems to be pointing to it being just a standard TO5, which really seems to be in the library, so I don't think there's actually a problem here. I think I can actually get pretty much straight to work. Yeah, so we want that one. 1, 2, 3, 4. Sanity check, comparing it against the bottom, the actual data sheet. So this is going to be a top. This is going to be a top view here, and this is going to be a bottom view because data sheet authors hate us. So this is going clockwise from the bottom, which means this should be counterclockwise from the top. Seems reasonable. You're saying that these holes are on a 5mm diameter. Over here, that looks like a 5mm diameter to me. You're saying that they're 90 degrees apart, which I agree with. And you're saying that you're going to need a 0.55mm drill hit. Survey says I don't even know. I mean, it's got to be fine, right? What could possibly go wrong? Worst case, we burn 30 bucks at Osh Park. We find out that this footprint is wrong. We will probably find out that several other footprints are wrong. Learning will take place. And the lesson, ultimate lesson at that point would be, don't trust your board layouts footprints. A lesson learned most painfully by so many people. Okay. So we want to associate parts. Right there. We would like TOSO through hole. Right. Nice hierarchical system that doesn't actually work once you're here. Instead, going to scroll through all of it. TOSO packages through hole. TO. Yeah, don't you like this? That the sorting in this giant list of all umpty-odd thousands of packages is like based on the actual number, right? And so 5 sorts before 11. But in the footprint editor, it was sorted on raw ASCII characters, in which case 11 sorted before 5. It's quality stuff we got here. Yeah, that's it. We're probably going to want some mounting holes. Hole. Mount. I can never remember. Oh, what is called? Right, because man, it just keeps doing that. I'm really sorry. So, look at the Raspberry Pi here. We're going to want the header to, we're going to want the board to plug into that header, and then we're going to want, ideally, we want the 4 mounting holes there, right? I mean, we'll see how that goes as far as actually going there, but to do that, we're going to need mounting holes. I'm not at the moment remembering exactly how to do that. So we're going to pull up some other project here. Nope. How about Arduino? Nope. How about PCB? And in this other project where I successfully got mounting holes, we're looking for these things. What are these under? Mounting hole pad. Isn't that what I was looking for? But anyways, mounting holes, which apparently is a whole entire footprint library. Mounting holes 2.7, M 2.5 pad VS, my favorite. Alright, because the Raspberry Pi uses M 2.5 holes. Yep, we want to close that one. Alright, so it should be under mounting holes. Device? Nope. Is there a whole mounting library that I don't have? My frustration is mounting. Oh, I'm just showing you my face. Sorry. Anyways, component libraries. Add. Mounting. Mechanical, maybe? Well, it's a new one. Maybe it's under device. Oh, that one's already in there. Mechanical. Heatsink. Mounting hole. Look at that. Look at that. Boom. 1, 2, 3, 4. I don't think this thing warrants a value. It has to have a value. Nope. Stop. Stop. Oh God. Let's assign all of them. Book. Okay. Mechanical sockets. Mounting holes. Oh yes. Yes, that's good. So the regular expressions on the mounting holes is actually set up incorrectly, so it does not give you any options as far as what mounting holes you can use, which is fabulous. Yes, I remember this issue. So you actually can't use whatever is that? What is that tool? CVPCB. You can't use CVPCB. You instead must edit the device individually and manually assign the mounting holes hole footprint. So If we wanted just a standard boring hole, we would want this one. I like this one because in addition to the main hole, which is the center one there, you've got all these additional holes. And what those holes do is it stitches the top copper and the bottom copper together, and it stitches the FR4 with all these extra plated holes. So it kind of makes it a more structurally robust part of the board. Not that that matters if you were to start depending on that sort of structural rigidity on your mounting holes on a bloody sensor hat. I would question what you are doing with your Raspberry Pi sensor hat, but these are our choices that we make. Come on. Assign footprint, that one. Fantastic. So now I need to additionally add grounds. Because that is what I want. I want all of this stitching tied to, like so. If I were to now run CVPCB to check all our footprint assignments, you would notice that these mounting hole pads are now correctly assigned mounting holes, mounting hole 2.7, M 2.5, pad via. Not possible from this tool, but it shows it to you, which is a nice sanity check. There we are. So in some ways, we could say that we're done. Mainly by just crossing out that which is not done, because at some point you just got to lay it out and go with it. And that's exciting. Let's just check all the stuff on the side. Check the chat. I don't think anything is happening in the chat. And away we go. Generate netlist. Generate. Generate. Go. Okay. Welcome to our board. So first thing I want to do is check the page settings and pull ourselves over into America. Set that stuff up, and I like that. And then let's start importing the netlist. Read current netlist. Seems reasonable enough. Oh, sweet Jesus. Right. So there is some trick. Till you can toggle into a mode. Scatter? Fantastic. There we go. Boom. So admittedly, compromises were made. You'll notice that many of these packages, like for example for this GPS breakout, is not actually a specific package for whatever GPS breakout I picked. It is a 5-pin 100 thou header footprint, because that is sufficient to support 5 thou 100 thou header, which is what this module goes into. So compromises were made, far from ideal, and for that I am deeply sorry. So we're first going to want to draw a board outline. Grid. Let's do something nice and coarse. And then so what I'm looking for is down here, you got the X and the Y. I kind of like to line it up somewhere nice and coarse. And man, I'm really just blanking out on this, aren't I? Oh, what is the board outline called in KiCad? Courtyard, margin, edge cuts? Edge cuts. We're on the edge. We're also in metric. Forget that nonsense. Six and 2. I don't even really know how big I'm trying to make this. That's where calipers come in hand. Because yes, I could go find the specs for Raspberry Pi and be disappointed, but it just seems easier to measure them. And say I want a board that's about 2.5. See how easy that was? So leave that at 6. 2 plus 2.5 would be 4.5. Survey says, boom. All right. How wide do we want this board? Raspberry Pi is 2.2 inches. 6 minus 2.2 would be 3.8. Boom. And boom. Does this seem like a reasonable start? So we're just roughing this stuff in at this point. Okay, well, this may require a bit more care than just kind of roughing it in. Let's give ourselves a more flexible grid here. Man, that is tight. Whoa. I kind of feeling like I didn't get that quite right. Like perhaps we want the board to be a little bit bigger than that. All right, let's find a graphical drawing of a Raspberry Pi. And Adafruit delivers. Does that look like a Raspberry Pi? That looks like a Raspberry Pi. Of course, their mechanical drawing is rotated from ours. I'm not committed yet. They're also centroid based, which is all sorts of lovely. So what I'm looking for right here is trying to figure out like exactly where these holes are in relation to primarily the header here, because that's about the one we really care about. And so we can see that the centroid of this 2x20 header is 29 millimeters from that hole, which presumably is in line. Do I believe that? Yeah, I would believe that. Okay, so apparently those two mounting holes are in line. That's somewhat actually surprising. And then you can see that the two mounting holes are 58 millimeters center to center, which means that the Raspberry Pi header is dead nuts between those two mounting holes, which I also believe, looking at this Raspberry Pi. So that's actually kind of a fun little fact I didn't know. Of course, my footprint isn't going to be based on the centroid, which is going to be a little bit awkward. And then in the other direction, excuse me. In the other direction, it's 49 millimeters center to center, whereas the board is 56, and the holes are inset 3.5 in each direction. So you remember how I said, you know, to hell with this metric thing, we're going English? We are running straight back to metric. Except now my holes here are probably a hot mess. Yeah, so see now all of my board outlines and everything are all set up in English, which is a royal pain in the patoots. So I'm going to open up the mechanical drawing on my other screen here. And we're going to sit here and we're going to start roughing this stuff in. Because what, 0's up here? Yeah. 50, endpoint 50, and then we're going to say, tell you what, let's start at 50-50, and then endpoint is going to be 56 millimeters greater than that, so it's going to be 106. Right, so that's jumped up there, but bear with me here. There we go. Start point 50-50. X dimension, we're going to be talking about something on the order of 58 plus 3.5 plus 3.5. That's 765. Nope. try that again with, you know, arithmetic involved. $50. The board, sorry, the hole center to center is 58. The holes to edge is 3.5. That's 65, but our origin is 50, so that's going to be 115. Let's try that on for size. Fantastic. And so now we just need to transcribe all those. So 106 from 50 to 115 or something. Yeah. Starting point X is 50, starting point Y is 106, end point is 115, and end Y is 106. Alright. X is 115, Y is 50, end point is 115, end point is 50. No. Y would be 106, like that. So I have managed to successfully back calculate that. I want this position to be 50 plus 3.5, 50, 3.5. Oh boy, now I've really done it. I'm trying to hold about 6 numbers in my head at once, and that's just a bad plan. So we want these inset 3.5 from 106 and 115. So we're going to want these in permutations of 53.5. Uh, 1.5 plus 3.5 is 15, or 5 plus 10. I hope you guys enjoy watching me mumble these numbers as much as I enjoy trying to do arithmetic in my head. X is 115, 53.5. X is 111, 102.5. X. Boom. Glorious. Look at that. Isn't that nice? I like that. Now this mechanical drawing has the header at the top, which I'm not morally opposed to. So I think we're going to rewrite our history here and drop it about there. But of course, this dimension is based off of this centroid here, and our location, our coordinate system is off of that, presumably off the center of the number 1 pad, right? Yes. See how that moves with that? So the question is, given that the centroid is 29 plus 3.5, which is going to be 32.5. So I know that the center here is 32.5 from the edge and 3.5 up. This coordinate here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 95 thou to the left of 32.5 millimeters from the edge. 95 thou. Dear God. Calculator. 95 times 25.4. 950 thou. So I know that this hole here is 24.13 millimeters from here. And that hole is 32.5 from there. 32.5 minus 24.13, 8.37 plus 50. So, in theory, no. In theory, no. X direction. So it's actually pretty close. I'm not entirely convinced that's correct. Really not. Yeah, 32.5 minus 24.13. So, stupid question. What if I say okay, so stupid thought. Let's zero off the offsets. Oh. No. That's the offsets for the label. That's not exactly not what I need. I mean, those are the numbers I need. Right? All that work I went through to count out 950 thou and then convert to metric, 24.13. Sanity check. X is 111.5. 111.5 minus 53.5 is 58, which is correct. 58 divided by 2 is 29, which is correct. So maybe it's not even that point, but is like that point, making this even less useful. Oh, well, whatever I did right there was definitely not what I wanted to do. Right, because I'm definitely moving just that one. What in the world? Can't find the handle for the... There we go. Lord. Okay. So I think this should be, this is positioned for the entire footprint, which is what I was trying to edit originally. And then, nope. I want 1.27 beyond 3.5 beyond 50, which is 54.77. Shut-up! Look at that. And there, ladies and gentlemen, is Raspberry Pi outline. Something that I probably could have pulled out of some library somewhere, but I trust no one as far as components like this. So there it is. We've done it ourselves. Now, if we really want to go crazy, we're going to want a 0.5 millimeter grid like that. Because those rounded corners, man, it really pulls everything together. It's probably not ideal that we've got, you know, multiple board outlines going on. Nope, that's wrong. It's probably not ideal that there's two of them, but I could certainly hope that Oshpark could sort it out. And, you know, it's like 11 o'clock, so it's cool. There we go. So now we just got to start mocking stuff in as far as where we think this stuff's going to go. Okay. So where do I want to put this ADC header? So the USB power is like right there. So maybe if I have the GPS receiver dangling off here on the side opposite from Ethernet, it might make some sense to have, I don't know, some random ADCs hanging off there. And I think we just start laying down the rest of the stuff wherever we want it. Try and get the stuff remotely closer to where I'm working. So these are my pull-up resistors on the I2C bus. That's part of the voltage divider. That's part of the voltage divider. That's also part of the voltage divider. So what I'm doing here is I'm just trying to sort these things by pin location here, and so that routing them is going to be a whole lot easier once I try and commit to it by having a nice fan out there. And that's what the sensor for there. Okay. And that's my get out of jail free card pin for that. Because, you know, something's on the bodge wire. Okay. Oh boy. So I want to be careful that I don't try and hang anything off this side, because this side is USB and Ethernet jacks. But I would kind of like to get all of my resistors in one nice line. And so if I were to dump that down there, it might make sense for this one to be on the far side, where those two could be on the near side, and then all these could be in the middle. So ready, set, go. Let's give me a coarser grid, so I stand a better chance of dumping these things on even spacing. One nice long run of resistors down the center. Okay. Oh, look at that. Isn't that nice? I think that's nice. Isn't that nice? One nice... That's what? 200 thou between each one. That's a nice, easy, luxurious spacing. Could probably bunch that up a little bit if I wanted to, but I kind of don't. That's nice. My silkscreen's a bit of a hot mess, and routing the the SPI bus back across that's gonna be a bad time. As is everything here. Right, these are only daughter cards. No recollection on which orientation the daughter cards are. But let's say that they're hanging off back here where the HDMI is. What does that get us? And that's just a bodge wire spot. Well, I certainly think that that board is doable. I'm probably going to really regret spacing these out so much, so I probably want to pull these in to like 150 thou spacing or something, so that each resist, like this one falls like halfway between them, just to bunch them up a little bit so that I have a nice window over here to kind of try and route stuff back up to the header, because I don't think I'm quite that good that I can and I now realize I probably have all of the voltage divider resistors here backwards. Right. See, what makes me nervous is when you start seeing lots of crossing like we have right here. That indicates that one side or the other is in the wrong order. And I'm willing to bet the easiest way to fix that is to swap these sets. Right, so now see how that line, and that line are no longer crossing? That indicates muy bueno, more better, less awful. And also has reduced the crossing down there. So again, we're starting to pick up less bad smells. I now notice that the BME 280 is an I2C device, so it likely makes more sense for us to put it closer to the rest of our I2C stuff here. GPS is UART based, so I think we might be screwed on that regardless of how where we position it. Gonna dump that out there just as a, just in case I goofed and misinterpreted the total lack of documentation on that pre-pin. And then these two LEDs are literally just because why not have spare LEDs to indicate stuff. More blinky is more better. So they're relatively loose on the whole use. Yep. Maybe kind of halfway between. Don't want to put them too close to the resistors because there's going to be a ton of the silk screens going to be coming out. Even that might not be good. More blinky is more better. Because you could have like some sort of heartbeat or like an error or network connectivity. You can have these two LEDs indicate anything that you want. Anything you want. So this hat's going to be hanging over this way. I'm going to have to figure out what the GPS board orientation is to make sure that it's going that way and not this way. So we're taking advantage of stuff hanging off the side of these Pi boards, because these are like at least for this first iteration, we're kind of looking at doing our testing like in, you know, windowsills and data center racks and places that we're not enclosing these things because, you know, prototypes, where ideally later it'll be something that you could actually enclose somehow. Not that that really makes that much sense since these are all like environmental sensors. But I'm going to say that that's a viable board layout. And if it weren't for the fact that it was already 1120, we could start actually laying down copper. But I think this is a good start. We're like halfway there. Got the hard part down, which is deciding where we want to put it. Now it's just running all the traces and stuff, which is, for me, usually goes pretty quickly since I'm locked in on the actual pinouts. Because it's not like we've got like a micro. Is like when there's a microcontroller involved, I spend all sorts of time remapping GPIO pins. But I think we're pretty much set there. So thanks for watching. I hope you guys all had a good evening. For what few of you were sitting here watching me, and I will try and remember to live stream when I'm actually laying down the copper. So there will likely be a second episode in this where we actually do that which was advertised tonight, which is actually lay out the board. So good night, and I shall see you guys later. Stop streaming.